Hello, Math 201. We continue with our series of derivative techniques lectures. And today we're going to talk about trig functions. And so before we start this lecture, I just want to remind you that having a background in trigonometry is a prerequisite for this course. And I hope that you remember what sine and cosine functions look like and that you'd be able to graph what a sine function looks like, a cosine function. And you know how to work with those functions. It's a prerequisite for this course, and so I won't spend a whole lot of time on it. The book does have resources in chapter 1, and so maybe I'll remind you. So look, or maybe I'll say it like this. Trig, background, expected. Chapter 1 has some I guess refreshers, so I will say that you need to know trig, and that it's expected you have a trig background, but if you need some refreshers and reminders, chapter 1 has that. Okay. Derivatives of trig functions. So we're going to take derivatives of trig functions. Our main goal today is to find the derivative of sine of x. And the derivative of cosine of x is very similar, but we're going to focus on this one, and I'll just tell you what that one is. It will be, I will go through some proofs, but I'm going to go through them for the sake of time again, kind of fast. But they're just good things to see and know, but I won't ask you to be able to reproduce them. In order to find this derivative, we're first going to focus on this derivative specific point. The reason being is that this limit will actually help us find all the limits when we want to find the limit for any of them. And so the idea is that if we let f be sine of x, then the derivative at 0 is the limit as x approaches 0 of sine of x minus sine of 0 over x minus 0, right? That's the definition of the derivative at a point. And so using that fact, well, we know what sine of 0 is. Sine of 0 is 0 and 0 is 0. And so the derivative at 0 is just the limit as x approaches 0 sine of x over x. If you try plugging in 0, you get indeterminate form. It's 0 over 0. But because it's sine of x, we can't factor and we can't conjugate it. And so we have to do something a little different. To try and calculate what this limit is, we're going to use some geometry. So what's going on graphically is if you graph this function sine of x over x, it looks something like this. It has a hole at 0 because it's not defined, but it looks like it's getting really, really close to 1. And we're going to use geometry and the squeeze theorem, which I think I might have brushed over, but I'll remind you what it is, and we'll prove it. So the key idea here is we have this triangle right here. The unit circle is this right here, and we have some triangles. And the idea is that the area of this triangle right here, area of OAD, is 1/2 cosine x times sine of x, because the distance, the x distance right here is cosine of this angle, and the y distance is sine, and so it's 1/2 cosine x times sine of x. Then the area of this bigger triangle, this distance is 1, and then this distance is actually tangent of x, because BC, this length over OC is equal to tangent of x, right? The tangent is opposite over adjacent. And so that means BC is tangent of x times OC, but this length is 1. And so it's just tangent of x. And so that's why this length is just tangent of x. And so the area of this bigger triangle is 1/2 1 times tangent of x. The area of OAC, this sector right here, remember the area of a sector is 1/2 r squared times theta. That's just 1 times 1 squared x. And we have this kind of squeezing, we have these inequalities that this triangle is always smaller than this sector is always smaller than that triangle. So we have those areas like that. That gives us this inequality, that 1/2 cosine sine of x is less than 1/2 x is less than 1/2 tangent x. So that's 1/2 sine of x over cosine of x. So what we can do is divide every single thing by x, and we get, or by 1/2 x, because they all have 1/2, and you get cosine of x is less than x over sine x is less than 1 over x. And then what we're going to do is we're going to flip everything, and it flips so if we take the reciprocals of all of them, then you get 1 over cosine x, sine x over x, and cosine of x, and that flips the inequalities. And this works for any angle between 0 and pi over 2. So x was any angle from there to there. We can do the same argument for an angle between, or down here, draw the same triangle and do the angle from negative pi over 2 is less than x is less than 0. And so we can take the limit as x goes to 0 of all things. So take this whole string and take the limit as x goes to 0 for all of them. The limit as x goes to 0 for cosine of x is 1. The limit as x goes to 0 is what we care about. And the limit as x goes to 0 of cosine of x on this side is 1. And so therefore, by squeeze theorem, the thing in the middle also has to equal 1. Because remember, if you have this kind of string of inequalities, you can take the limit of the left thing and the right thing. And if they equal the same thing, then the thing in the middle has to be the same as well. And so the idea is that this limits to 1, that limits to 1, then the thing in the middle has to limit to 1. And so we get the inequality we need, or the limit we need. And so the limit as x approaches 0, sine of x over x is equal to 1. And so let's record that. So the limit as x approaches 0, sine of x over x is equal to 1. Similarly, the limit as x goes to 0 of cosine x minus 1 over x is equal to 0. The proof is in the book. It's kind of fun, but I won't assign it or anything. But if you enjoy math and kind of like fun puzzles, it is a fun little trig puzzle. And so these inequalities these limits are actually interesting in their own right. And so let's kind of look at this. We can use it to calculate a limit like this. The limit as x approaches 0 of sine of 4x over x. So this is sine of x over x. So how can we get this to kind of look like something over something where that thing is going to 0? And the idea is we're going to multiply the top and bottom by 4. If you multiply the top and bottom by 4, then this 4 we can pull outside and put it right there. And then sine of 4x over 4x. Sine of 4x over 4x, if we think about 4x and 4x, that and that are the same. And so as x goes to 0, those things are also going to 0. And so because it's the same thing over the same thing, right? 4x over 4x, we can just say that this really will go to 1 as those things go to 0. You can also do a kind of a substitution and say let t equal 4x. Then as x goes to 0, t will go to 0, right? If x is going to 0, then 4x will also go to 0. And so this is 4 times the limit as t goes to 0 sine of t over t, which we know at that limit, that's 1. So it's 4 times 1, which is 4. And so that's one way we could do it. Another type of limit we could do is if we have, maybe I'll erase this real quick. So let's say I wanted to calculate this limit, sine of 3x over sine of 5x. Well, I can multiply top and bottom by 1 over x, both of them, by 1 over x. 1 over x. And then I get the limit as x approaches 0 of sine of 3x over x and sine of 5x over x. Then I can multiply top and bottom by 3 there, top and bottom by 5 there. And then pulling out this 3 and pulling out this 5. And again, I can split this limit up into the top and bottom by the limit laws. And I get 3 over 5. And then the limit as x approaches 0 of 3 sine of 3x over 3x, where that matches that, and that matches that. And as long as the thing is going to 0, because that's going to 0, that's going to 0, that's going to 0, then this will equal 1, that will equal 1. So I will even say that. So this equals 1, that equals 1, and we get 3/5. And so there's going to be a couple limits like that on the homework to play with. The idea is if you have sine of something and the same, and you can somehow get the same thing on the bottom, pull out the other stuff outside of the limit, and then the limit of the sine of something over the same thing. So the limit as u goes to 0 of sine of u, where u is just any sort of expression, and u, as long as this and this are the same, and it's going to 0, then this will always equal 1, no matter what u is. And so that will be what you'll need for the homework. And so those are important in their own rights. But now let's use it. We're going to use it to prove what the derivative of sine of x is. Our claim is that the derivative of sine of x is cosine of x. And the way we can kind of do that is by looking at the graph of sine of x. If you look at the graph of sine of x, the derivative is positive and then 0, and then negative 0, positive 0, negative 0. So it's kind of cyclic. And so it's positive 0, negative 0, positive 0, negative 0. And so the derivative is cosine of x, and we're going to prove it. And the way we're going to prove it is by the definition. Remember, so if f of x is sine of x, then f prime of x is the limit as h approaches 0 of sine of x plus h minus sine of x over h. But using the sum formulas for angles, sine of x plus h is sine of x cosine h plus cosine x sine of h. So plugging that in for sine of x plus h, we get the following. It's sine of x cosine of h minus sine of x plus cosine x sine of h. I'm going to break this up into two limits. I'll split it up right here and split it up right here. The first one, I can pull the sine of x out because it's the limit as h approaches 0 and there's no h in it. And then I get cosine h minus 1 over h. But remember, we said that that limit's 0. And then on the other one, I'm going to pull a cosine x out, and its limit is h approaches 0, sine of h over h, but we said that that's 1. And so it really becomes sine of x times 0 plus cosine x times 1. And so it is cosine x. And so the derivative of sine of x is indeed cosine of x. So now we have the following. The derivative of sine of x is cosine of x. The derivative of cosine x is negative sine of x. The proof is exercise 83 in the book, and it's also fun. And so again, I'm not going to assign it, but if you like fun math puzzles, it's kind of a fun one to do. So let's take the following derivatives. The derivative of e to the x cosine of x. So y prime, by the product rule, it's the derivative of the first guy times the regular of the second guy plus the regular of the first guy times the derivative of the second guy, and the derivative of cosine of x is negative sine of x. And so you can write this as e to the x times cosine x minus sine of x. So that's a simple product rule. For this one, y prime, you take the derivative of the first guy, which is just cosine of x, and then minus, then we have to do the product rule here. And so the derivative of the first guy is 1 times cosine of x plus the regular of the first guy, x, times negative sine of x. That's the derivative of cosine x. Now we can distribute, and you get cosine of x minus cosine of x, and then it will be plus x sine x, because that minus sign distributes to that minus sign, and we get a plus. And so this just equals x sine of x. So the derivative of x sine of x is sine of x, or the derivative of sine of x minus x cosine x is just x sine of x. Okay. And then finally, let's do this one. This one's going to require a quotient rule. So y prime is going to be, maybe I'll even re-record this so I have it so I can see it. Okay, so remember, we're going to use the quotient rule. So y prime is low, which is 1 minus sine of x, times the derivative of high. The derivative of 1 plus sine of x is cosine x, because the derivative of 1 is 0, and the derivative of sine of x is cosine x, minus, so it's low d high minus high, 1 plus sine of x, d low. The derivative of the low is negative cosine x, because the derivative of negative sine of x is negative cosine x, then all over 1 minus sine of x squared. And then that would be fine on an exam, but let's just simplify and see what happens. So I get cosine of x minus cosine x sine of x. And then this becomes minus cosine x, but then it's negative, so it's plus cosine x, and then this times that becomes plus cosine x sine of x, plus cosine x sine of x. So that will cancel with that, all over 1 minus sine of x squared. So our final answer is going to be 2 cosine x over 1 minus sine of x squared. And so that's what the derivative is. And now we can use the derivative of sine and cosine to derive others. So for instance, let's show that the derivative of tangent of x is secant squared x. The way we're going to do that is we're going to take the derivative d dx of tangent of x, but tangent of x is sine of x over cosine of x, right? Tangent is their ratio. And so by the quotient rule, it's low d high, so cosine of x times the derivative of sine of x, which is cosine x, minus high sine of x d low. Sine of x d low, which is negative sine of x, all over low squared, cosine squared x. And so what does that equal? That becomes cosine squared x plus sine squared x over cosine squared x. But we know that cosine squared x plus sine squared x, that equals 1 by Pythagorean identity. Cosine squared plus sine squared, that equals 1 by Pythagorean identity. That's a very important identity to know. And so this equals 1 over cosine squared x, but 1 over cosine, remember, is secant. So this is secant squared x. And so that's how we can use the cosine and sine to get the other trig ones. And you can do the same thing to find all the other ones. And so we have 6 new derivatives: sine, cosine, and the derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant tangent, and derivative of cosecant is negative cosecant cotangent. Actually, I wanted to do this example. Let me erase this real quick. So let's do one final example. Let's find f prime of x. So the way we're going to find f prime of x is by the quotient rule. So f prime of x by the quotient rule is the derivative of secant x, which is secant x tangent x times the regular of the second guy, which is cosecant x, and then plus the derivative of the regular of the other guy, secant x, times the derivative of cosecant x, which is negative cosecant x cotangent x. And so as it's written, it's not super pretty. And so what we're going to do to simplify it is we're going to write them all in terms of sines and cosines. And so this is 1 over cosine of x. This is sine of x over cosine of x. And then this is 1 over sine of x. And then plus, this is 1 over cosine x. This is negative 1 over sine x. And then this is cosine x over sine x. And so that cancels with that cancels with that, and we get 1 over cosine squared x minus 1 over sine squared x. And so we could leave it like that, but we know sometimes we like to undo the fractions. And so we'll just write this as secant squared x minus cosecant squared x. And so I don't know if it's obvious from looking at that that's what that is, but if you write it in terms of sine and cosine and then simplify and then redo it, then you can get it. And so that would be what the derivative is. That's the nicest form of it. And so the derivative of secant x times cosecant x is secant squared x minus cosecant squared x, using just the product rule and some trig substitutions. All right, that should be all you need for your homework. I'll see you guys next time.